values, okay, if these values are actually discrepant in this way, then this variable is related to this variable. Meaning being male or female is going to determine whether you end up watching tearjerker movies or action movies. Does that make it a little bit more comprehensible, given, this is a 2x2 chi-square. It's easier to sort of grasp fully. And the example is better. It's more intuitive. Thank you for suggesting that. OK, so that is basically it. I still have 10 minutes. Don't go away. I still have 10 minutes. So this is the chi-square. So for the people who are going to be just doing the test, doing the examples, you're just going to do one ANOVA and one chi-square, and you go out of here. It will take you half an hour, and you're done. For everybody else, sorry? Yeah. I know. I have 3 people getting. Did you get 95 on every and each test? No. So it's not favoritism. It's fair. And now, and the other thing is, for the other people, you need to really review everything. Everything that we've talked about should, by now, hopefully make sense. You should know variances and how they interrelate, how they work in different tests. So you need to understand things conceptually. You've seen the tests that I've given you. I have a very, very important suggestion that I will make that will help you really put things together. And it will really make this course actually. Oh, thank you. Thanks. You're moving with me. This is the poster I started out the semester with. And now it's actually a poster that's in your book. It's at the end of your at the end of the let's put it here. Here we go. And then we'll put these guys. I know you might not be able to see things very clearly, but it's actually in your book. So if you open your book to the cover, you're going to see these here we go. And where's my book? OK, so this is actually from the back of your book. What I'd like you to do is actually take a final look. Before you come to class and as you're studying for this, just take a look at where we were and what we've developed. And you're going to see one more time the five steps of hypothesis testing. But you're going to see how at each level we changed one minor thing. And let's just go through that very quickly in 5 minutes. We started out with the z-test for a single sample. We started with a single baby, right? And you understood from that single baby that the fundamental question we're asking in hypothesis testing is how extreme is this score? Is this score extreme enough that we cannot simply attribute it to an error in sampling? That we didn't just pick a single baby who walked at the age of 7. That is very unlikely just by chance for us to randomly select a single baby and that baby walked by the age of 7. Remember that story? Well, if that's the case, then we can reject the null. So you've understood this concept of rejecting the null. It's based on that principle. But then we moved to the next chapter. We were dealing with single babies. We moved to the next chapter, which is chapter 6. And in this chapter, we took the idea of the single baby and we developed the concept of a sample. And instead of our comparison distribution being just simply a population of single babies, we compared it to a distribution of means of single babies, depending on the sample size. Like if we took five single babies and we calculated their mean, we had to use a comparison distribution made out of babies, 5 babies every time. And that distribution is a distribution of means. So in this chapter, we came up with the concept of distribution of means, and we figured out how to calculate it. So do me a favor and actually do look back at that demo I showed you. Go back to it, play with it, because it will reinforce the concept and you'll really benefit. Anybody taking an advanced course in statistics or going to graduate school, if you do that, I promise you, you'll really be ahead. So we've got the concept of a sampling distribution. And as Arian today mentioned, the sampling distribution is dependent or proportional to the original distribution depending on the sample size. So the bigger the sample size, the narrower the sampling distribution. We moved from there. This was the z-test. This is where you actually had a population that you knew the population parameters. We moved to another type of test where we didn't necessarily know all the population parameters. We removed one population parameter. We started out by removing the mean, or the variance, excuse me. We removed the variance, and we had to estimate the variance. So in Chapter 8, we added this concept of estimation. And the concept of estimation is all around the degrees of freedom. And what was the degrees of freedom? It was that method to assess the precision of your estimate. It allowed you to keep track of how much error you're introducing into the system when you estimate. The bigger the sample, the bigger your sample, the less error you're going to make in your estimation, the more accurate, the more like real knowledge of the population. And the smaller the sample, the more error you're going to have. So you use the degrees of freedom as a way to keep track of your error. And then you account for it by making your cutoff scores higher and higher for more error-prone. When your sample is smaller and you have more error, you want a more extreme cutoff. And that's why you have a t-table. A t-table has broader or thicker tails, which means you have to find an more extreme score to be able to reject the null. So that was the concept we introduced here. And we did two things. We did a single sample t-test, and then a t-test for dependent means, where you looked at before and after. Okay? A single sample t-test where I basically gave you the mean and the mean of the population, but didn't give you the variance, and you had to calculate the variance, and you compared it to 0. You compared the mean to the mean I gave you, and here you compared the mean to 0. Under the null, the before and after should be 0, and therefore you compare it to 0. Everybody with me? I'm just sort of going over this to just refresh your minds. Then we moved to the independent t-test, where we basically took what we've learned here and just doubled it. We created two distributions. We estimated 2 original populations. Then from that, we pooled things, and then we created sampling distribution, and then we calculated another comparison distribution that is a distribution of differences between means. Remember? So your sampling distribution here was simple, which is distribution of means. Here it was SDiff. Remember SDiff? SDiff is a sampling distribution of differences between means. Here it was the sampling distribution was a sampling distribution of different scores. Here it was single scores. Then we moved from there and did the analysis of variance. And with the analysis of variance, we switched ways of thinking. We stopped thinking about comparing means directly, and we moved into the idea that you can compare means or say that the means are different by using variances, sort of an indirect way, like going around, using variances to make a statement about the means. And we used a concept that we did here, which is the S-pooled. We now call it S-within, right, which is exactly like S-pooled. But we introduced the concept of S-between, the variance between, S-squared between, excuse me, S-squared pooled and S-squared within. So we introduced the concept of S-squared between, which is a new concept, which results from calculating the S-squared of the sampling distribution and then multiplying it by n, sort of getting the original population, then getting the F ratio. And after getting the F ratio, you then can decide to reject or not reject the null. And finally, this is what we did today, which is the goodness of fit test, which I don't need to repeat because I just told you. But these two techniques are techniques used for categorical data. Everything we've used up to now had been for continuous data, for data that is either interval or ratio. Now, from this point here on, the chi-square is categorical data. And it's done by using this sort of measure of discrepancy. How different are these scores from each other? How different are these percentages from each other? You calculate the chi-square, and then you compare it. You calculate an observed chi-square from your sample. That's your observation is from your sample. And then you calculate a cutoff chi-square, or what you would use as your cutoff. And then you compare them and say, oh, yeah, these are independent variables, or they're dependent on each other. That's the test of independence. Or, oh, yeah, my variables or my group actually fits very well with a group I have, like census data. So that's a goodness of fit. So that's overall the whole semester. And you can see we really moved step by step. Okay? So in your review, try to see it as being a build-up to this point of ANOVA. Arian.
You said so the last two were categorical. What was it? This term you used to describe?
So it was a categorical test to test things that are nominal. Remember, we had nominal, interval, ordinal, interval, and ratio data. Remember NOIR? Okay. You use the test ANOVA and t-test and z-test for data that is either interval or ratio. Okay, meaning continuous, meaning that their levels of measurement are continuous, like length. You can find a length that is 6 meters, or 6.2 meters, or 6.2223 meters. You can go into the intervals in between, and those are meaningful. So that is a continuous variable versus categorical. Male, female, there's no in-between, right? Or religion, there is no in-between. You could philosophically talk about in-betweens, but practically there's no in-betweens. They're categories. And that's what you use the chi-square for, category, and everything else you use the ANOVA. You use for the categorical or nominal, ordinal, categorical are nominal or ordinal. Those you use a chi-square. And for interval and ratio, you use the ANOVA and t-tests. Yes?
How are the tests? How's it going to look?
How is the test going to look? It's exactly like the test you've seen, but it covers everything. So there is no holds barred. 40 questions.
And then
two solved problems. So for the people who have done the 95, 95, 95, they don't have to do except two. Other people might have to do a t-test, a z-test. It's up to me. So there might be more than two for people who. Yeah. So review.
How many math problems are on the test?
How many math problems? There could be 3. For the general populace, it could be 3. But for the people who have achieved the 95, 95, 95, it's only 2.
Okay. But for the rest of us, it's 3.
Yeah.
And they're all from this chapter 9.
No, they could be from anywhere. The solving the problems could be from anywhere. Because really, if you don't know how to solve a Z, you probably don't know how to solve a T. You probably don't know how to solve an ANOVA. So let's face it. Yes?